In this video, we're going to look into recursive rules with sequences. So far, what you've learned to write sequences with is something called an explicit rule, which basically, if you have an explicit rule, that is going to give a sub n, your nth term, as a function of the position n. Basically what that means is if I tell you what the position is, like the third term, or if n is 3, I can plug in 3 into my definition or my rule and get the third term. So just for example, this is what I mean. Let's say I define my nth term as being 2 times n plus 2. So if I wanted to know the first term, I would just basically plug in 1, the n value, or the position number. So it would be 2 times 1 plus 2. My first term would be 4. If I wanted the second term, I would just simply plug in 2 and do 2 times 2 plus 2, which would be 4 plus 2, or 6. If I wanted the third term, it would be 2 times 3 plus 2. It would be 6 plus 2, or 8. And I can easily jump to, if I wanted like the 10th term, I can do 2 times 10, add 2, which would be 20 plus 2, I'd get 22. Now, that's what we've been familiar with. There's another way of defining a sequence, and it's called a recursive rule, or defining them recursively. Basically, what you have to do is, you have to know a few first terms of a sequence. So this would be given the first term, and sometimes they'll give you more than one term, so I'm going to put terms in parentheses. So given the first terms of a sequence, a sub n is found by relating to previous terms. So you can't simply plug in, let's say I want the 10th term and plug in 10 and get it. You have to know the preceding terms to that 10th term. So for example, let's say I defined a recursive rule as follows. Let's say I tell you that my first term, a sub 1, is 4, and my rule is a sub n equals a sub n minus 1 plus 2. So just to kind of show you how this works, if I already know the first term is 4, so if I wanted to know my second term, 2, that means I'd have to know the term previous to it, or a sub 2 minus 1 plus 2. So my second term would be really a sub 1, 2 minus 1 is 1, plus 2. So to know the second term requires me to know what a sub 1 is. Well, good thing they gave it to me right here. I know it's 4. So my second term is simply 4 plus 2, or 6. Let's write out the terms over here. So far, I know a sub 1 is 4, a sub 2 is 6. Let's do another one. Let's see if I can find a sub 3. So a sub 3 would be a sub 3 minus 1 plus 2. So that would be like saying I need to know really a sub 2, 3 minus 1 is 2, plus 2. So I need to know what a sub 2 is and add 2 to it. Well, a sub 2 I found over here was 6. So a sub 3 is really 6 plus 2. So a sub 3 is 8. Let's do one more. A sub 4, I would just jump to knowing this. If I look at my rule, it's always going to be the previous term added 2. So the previous term is 8, add 2. A sub 4 would be 10. I think you can see that these sequences here and here are actually the same. It's an arithmetic sequence, 4, 6, 8, Now the 10th term here I was able to easily figure out. Here, if I wanted to know what a sub 10 is, I would need to know what a sub 9 is and then add 2 to it. So it's not quite as nice and convenient as an explicit rule where I can just plug in any old term I want and get an output. Here I'd have to know a previous term. That's basically the gist of a recursive rule. Let's do an example of writing the first 4 terms of a sequence. So let's call this example 1. I would like to write the first 4 terms of the following sequences that are going to be defined recursively. So for A, let's say I have a sub 0 equals 1, and my recursive rule is a sub n is equal to a sub n minus 1 plus 4. So basically the rule is saying, okay, if I want to know a term, I have to take the previous term and add 4. So hopefully you get in the habit of looking. If I want the nth term, a sub n minus 1 just means the previous term, right? And then add 4 to it. So I already know a sub 0 is 1, so let's do a sub 1, the next term. So if I want to do that, I have to take the previous term, a sub 1 minus 1, and then add 4. Well, that is the same as a sub 0, add 4, which is 1 plus 4, so that would be 5. So a sub 1 is 5. Let's do a sub 2. So a sub 2 is just going to be a sub 1, add 4, the previous term, right? So if I want to know the second term, I take the previous term and add 4. So that's just going to be 5 plus 4 for 9. So a sub 2 is 9. Let me maybe circle the first terms here. So I have my first term is 1, second term is 5, third term is 9. Let's do one more. A sub 3 would be the previous term, 9 plus 4, which would be 13. So a sub 3 is 13. Now, I want you to notice, for this one, my terms going from one to the next increase by 4, right? I'm just adding 4 each time. I go from 1, add 4 to 5, add 4 to 9, add 4 to 13, and so on. Hopefully you recognize that this is an arithmetic sequence. So you can have a recursive rule for an arithmetic sequence. As a matter of fact, the rule is this. For an arithmetic recursive sequence, it's going to be the rule, a sub n, is going to be a sub n minus 1, the previous term, plus d. And d is still the common difference. So I would box that. That is something that we're going to use in our next example. So in here, it kind of fit that same formula, right? Here's that common difference for that example. It was just going up by 4 in that case. Let's look at one more example of a recursive rule. So let's say a sub 1 is 1, that's my first term, and a sub n is defined as 3 times a sub n minus 1. Basically, I do 3 times the previous term, right? If I want to find the nth term, n minus 1 is just the term before it. So, if I wanted to find a sub 2, I'm going to do 3 times the term before it, a sub 1, which I know is 1. So a sub 2 would be 3. If I wanted to know a sub 3, I would do 3 times the previous term, 3. So it would be 9. If I wanted to know my fourth term, I would do 3 times the term before it, which was 9. So that'd be 27. Now as I list these, the sequence is 1, 3, 9, 27. You can see each time I'm multiplying by 3 with a common ratio 3. This is a geometrically defined recursive sequence. So there is also a way of doing geometric sequences in this recursive way. Let's write down that rule. So a geometric recursive rule is a sub n equals whatever the common ratio is, r, times the previous term. It's actually quite simple if you think about it. It's just saying take the previous term and multiply it by whatever the ratio is. I mean, it's kind of a very straightforward way of thinking about a geometric sequence. You're just multiplying by the same ratio to the term to generate the next term in the sequence. Let's see if we can use an example where we apply these now. Let's make this example 2. Let's see if we can write a recursive rule for the following sequences. So for A, let's say I had 3, 13, 23, 33, 43, etc., etc., and let's let B be 16, 40, 100, 250, 625, etc., etc., etc. So, for part A, as we investigate this sequence, you might notice that every time we are just simply adding 10 to the previous term to get the new term. That means my common difference for this arithmetic sequence is 10, right? So I think that rule is just going to be a sub n equals a sub n minus 1 plus whatever that common difference is, 10. Now the only thing you want to also do here, guys, is you have to let the user of the recursive rule know, where do I start with? What's my first term? So you can say, all right, a sub 1 equals 3. You can say your first term is 3. Now what's also kind of interesting, you might have noticed in the previous example, sometimes the first term is not written as a sub 1. They would write like a sub 0 equals 3. It's really up to the user to define what they want the first term to be, whether it's a sub 1 or a sub 0. I often just use a sub 1 to mean my first term. It's, I think, a little bit more straightforward to think of a sub 1 as being the first one. So I think this works. If we start by plugging in 3 in there and add 10, we would get 13, and I think that would generate itself quite nicely. Let's take a look at part B. Now, as you investigate B, I don't think if we add, what would we be adding, was that 24 to 16? But if you add 24 again, we definitely don't get to 100. Let's see if this is a geometric one. To see if it's geometric, I think we have to do the common ratio. Let's divide 40 by 16. I think if you do that, you're going to get 2.5. And let's double check that this works for a few more. If I did 100 divided by 40, and you divide that in your calculator, I think you're going to get 2.5 again, and so on it will work. So this is geometric, and the common ratio is 2.5. So if we know that, to get the rule, all we have to do is, okay, our nth term is going to be 2.5 times the previous term, which we write as n minus 1, a sub n minus 1. So all I have to do is take the previous term, multiply it by 2.5, and I'll get the next term. And that makes sense. The only thing is I have to tell the user, where am I starting? What is my first term? So we know what to start multiplying the 2.5 by. So here we have to say the first term is 16, and then we can start multiplying away with that 2.5. Let's move on to the last thing that I want to show you, which is kind of the trickiest. Let's look at example 3, special sequences. And let's see if we can look at a few ways of writing the rules for these. Let's say I give you this sequence: 1, 1, 2, 3, 5, 8, 13, and on and on and on. Let's just look at that one for a second. The first thing you're going to want to try to see if you can use is, hey, is this arithmetic or geometric? But I think obviously to get from 1 to 1, we didn't add or subtract anything. The common difference right there is 0, but clearly to get from 1 to 2, we added 1. From 2 to 3, we added 1. Then we started adding 2, we added 3. This is not arithmetic by any means. So maybe it's geometric, but if you try to do the common ratio and you divide 1 by 1, the ratio there is 1, but if you look at the next terms and divide 2 by 1, the ratio turns to 2. So this is not geometric either. So I'm going to erase that. That's not going to work. This is a special type of sequence. We have to just think about, like, is there a pattern here like that we can see? And it's not very obvious sometimes, and sometimes it just takes some like struggling with or grappling with the problem and trying different things in your head. As I look though, and I try to relate this, it looks like if you add the 1 plus 1, the two terms together, you'll get 2, which is that term. And if you add these two terms together, 1 plus 2, you'll get 3. And if you add these two terms, 2 plus 3, you'll get 5. And if you add 3 and 5 together, you'll get 8. If you add 5 and 8 together, you get 13. So what it looks like is going on here, guys, is if we were to add the two previous terms together, we can get the next term. So that's not very obvious to see. So what I'm telling you is, again, if I wanted to know this term, 2 would be equal to the two previous terms added together. If I wanted to know, let's use a different color here. If I wanted to know this term, 3, it's just adding together the two previous terms, 1 plus 2 together. And that pattern does work. And that's, again, not very easy to catch on with, just looking at it and getting it right off the bat. It takes a little bit of time and practice. So the way I would define this is as follows. Let's say the first term is 1, and the second term is 1. We can define the nth term by adding together the two previous terms. So a sub n would be equal to its preceding term, a sub n minus 1, and then adding that to the preceding term for that would be a sub n minus 2. So those are going to be adding the two previous terms together. And if you wanted to check, let's say I wanted to know the third term, right? That would be adding a sub 2 plus a sub 1 if you substitute the n values in and subtract. So if I know those two values there, a sub 3, the third term is just 1 plus 1, which is 2, and that matches the sequence. I'm going to show you one more example of a special one. Let's say I have 1, 1, 2, 6, 24, etc., etc., etc. Now this one, it's definitely not arithmetic. I'm not adding 1 or something like that and being consistent. I'm not multiplying every time by the same number, so it's not geometric. So this is another special one, and to be honest, looking at this for a while is going to be tricky. So I'm going to show you a technique you can use that sometimes will help you see a pattern. Let's just say I start this one with a sub 1 and this one with a sub 2, and this is my third term a sub 3, and this is my fourth term a sub 4, and this is my fifth term a sub 5. Sometimes you can see a relationship between the actual position number and the terms of the sequence. So I don't know if you look at this one, and again, it takes a little bit of time to notice, but if you multiply together, let me erase those pink marks for a second. If I were to multiply together the actual placeholder, the n value with the term itself, I can generate the next term of the sequence. So for instance, if I multiply 2 times 1, I get 2. If I can multiply 3 by 2, I get 6. If I can multiply 4 by 6, I get 24. So clearly that's the pattern. It's now, okay, how do I describe that, right? Well, let's see if we can do it. If I know that a sub 1 is 1, the nth term can be generated by multiplying the actual value n times the previous term. So let's see, a sub n minus 1 is the previous term. Let's see if that generates the sequence as wanted, and we can make changes as needed. So if I wanted a sub 2, let's say the second term, then that means I'm plugging in 2 times the previous term, which is 1, and I don't think that worked, right? I would get 2 there, and I do want a 1. So I have to change something here. I think what we have to do is, oh, I know what we did. Remember, we multiplied the n value to the term of the sequence. So I'm going to change this for a second. I get to erase. Let me just use the eraser here. I'm going to erase this. Let's see if we can change this into the following. Instead of doing n, I'm going to do n minus 1 times a sub n minus 1. Let's see if that works. So if I want to do my second term, that'll be 2 minus 1 times the previous term, a sub 1, which is 1. So it'd be 1 times 1. That worked for a sub 2. Let's check one more. A sub 3 would be 3 minus 1, and then multiplied to the previous term 1. That'd be 2 times 1. I get 2. I think this is the one that I want. So again, these special ones are a little bit trickier to do, but I think the only way of getting good at those is by practicing and sticking to your guns and trying a few different things. And once you get the hang of one or two, it kind of reveals itself a little bit more. Here is your self-quiz. Please feel free to rewind and look at some of the previous examples or your notes to help you with some of these problems. So for the first two, you're going to just write out the first 5 terms of the recursive sequence. And then for number 3, there's 3 different sequences I give you. And I'll give you a hint. The first 2, you should be able to use a special formula for. And then the last one is kind of a tricky one, but I think the ones that I showed you were a little bit trickier. If you look at that, you might be able to figure out the rule for that. Good luck. Thanks for watching, and we'll see you tomorrow.